So welcome back. This is week number 2. And it's called one-dimensional uniform motion. One-dimensional uniform motion. So in physics, it doesn't take much to get things complicated quick. All right? So we start off with a classic motion lab where you study the motion of a uniform object, and then you can change what will make that uniform motion different, but then it'll still be uniform. It'll just be different uniform motion. All right? So while you're looking at this background information, so again, every time you look at our videos, there's 2 when you're online, totally online. One's called background, and then the other one is the experiment itself. Okay? And this particular experiment you're going to be doing at home. So I'm going to take you through it and show you how I do it here in the lab, and then you can come up with your own ideas with your group and then do the same thing at home. All right. So anyway, this is also called the tortoise and the hare race. So you know the old story where the hare figured he got this race all wrapped up so he could go take a little snooze. And then once he found out, whoa, I slept too long, he had to hightail it, and he ended up losing the race. So anyway, this good old Bugs Bunny being taken on by the tortoise, and you see the tortoise won. He collected his winnings, and that's all Bugs could muster up because he was angry. He should have won that race. See, he's over here going, nah, I beat him, but you see, he already got the money. So anyway, if you want to measure motion, the very first thing you need is the starting line. Now, uniform motion has been going on forever. So when you think of uniform motion, it's not like, oh, you start it and then you stop it. No, it's always been going. And what we do is we just take a slice of time and look at that kind of motion in that period of time. Because, you know, things like that really don't exist. All right. And that's what it says down here. Uniform motion has an eternal beginning and goes on to eternity. We have this thing called the past, the present, and the future. And time keeps on ticking, ticking, ticking into the future. So you see, time is not a vector. It only goes in one direction. All right, so you can't go flipping it around, flip it up, flip it down. No. It just keeps on ticking, ticking, ticking into the future. You have no control over it. All right. So, time. What is time? Well, it's an ongoing sequence of events. It involves the past, the present, the future, and it's a fundamental measurement. It's made in seconds. So the fundamental unit of measurement is the second. Little s. Not SEC, just little s right there. A span of time is called delta t, and you take your second measurement minus your first measurement. The first measurement came before, earlier than the second measurement. Time is a scalar, which means it has no direction in the 3 directions of space. Up, down, and in and out, or X, Y, and Z. Anyway, here's a definition of time, because it's hard to define time. But you can relate it to things in your life that involve time. Like time is slow when you wait. Time, you know, like when you were going on a road trip, what do you keep asking your parents? Or when are we going to get there? Huh? When are we going to get there? I need to go stop. Where's the closest McDonald's? Okay, you just, all this endless bickering in the back seat. Time is fast when you're running late, isn't it? And time is deadly when you're sad. And time is short when you're happy. Time is endless when you're in pain. Time is long when you feel bored. And so on. Every time is determined by your feelings and your psychological conditions, not by clocks. So have a nice time, always. All right. Time is a little bit difficult to define. But you can say, well, wait, what about like McDonald's fries? Man, I love those fries. And when you try to get your mind around what is it that you love, that is a tough thing to write about. Just try it sometime. Try to define what it is. All right. Position. Now we're only working in one dimension. Remember, only one-dimensional motion. Position is measured by a vector. Vectors are bold type. If you go back over here, you can see the little t over here is not bold type. See up here, bold, bold, bold. Velocity is bold. It's a vector. Time is not. Okay? So anyway, position is a place in space from some origin in one direction. So if you want to know your one-dimensional position, you got to pick a spot and call that your starting spot. And it's called your origin. You even do that with time too. You go right now at t equals 0, things are going to start, and we're just going to look off into the future. Now you can also calculate back in time, but generally you do an experiment, you start the clock, and then look forward. All right. So anyway, this is where we live in the Milky Way Galaxy. We're about 2/3 of the way out. We live in what's called a barred spiral galaxy. It's about 75,000 to 100,000 light years across. And it's about 4,000 or 5,000 light years thick. And these are dust lanes with lots and lots of stars. About 200 billion stars total, with a good number of them right there at the center. And at the very center, there's a very large black hole. Millions of solar masses. It's eaten millions of stars over its life, which isn't very big though. Some galaxies have 100 billion solar mass. But we don't live in an active galaxy. We don't have very many galaxies in our neighborhood. That's why we're here. That's why we're here. We wouldn't be here if we were in an active galaxy. There are only a few galaxies in ours. All right, so let's go back to the definition. It's a place in space from some origin in one direction. You go forwards or backwards. Fundamental measurement made in meters, little m. Now you engineers, you put a letter in front of that because the meter might be too big. So you use centimeters, micrometers, nanometers, okay? But still meters. A change in position has its own name. It's called displacement. And that's delta x, and that's x2 minus x1. Remember, delta is always the second minus the first. This is a vector, which means it has forward, positive displacement, and backward, negative displacement. All right, and then velocity is the rate of change of an object's position. Well, remember, the change in position of an object is called displacement. So it's displacement over time. So you can see right there, there's displacement over time. And if the velocity is uniform, constant. It doesn't change. And if you wanted to calculate it, you do delta x is x2 minus x1 over t2 minus t1. Now, if you solve this equation right here, and you call x2 x, and you call x1 x naught for the starting position, and down in the bottom you call t2 t, and you call t1 0 for t equals 0, then if you solve this thing, you get the equation that you're going to be using in the lab today. Okay? That's constant motion equation. All right. Now, we're almost done. I didn't show this on the first slide. So my son, when he was in my class teaching in Florida, I had a lab called My Aim is True. So they would take darts and throw them at these plastic darts, throw them at the plastic dartboard, and then they would measure the angle and the distance from the center of the dartboard, and they would do it 50 times, one person. So one lab partner had the extreme pleasure of making all the measurements, and then the other one had the drudgery of throwing 50 darts. So he would take some time throwing his darts till he got his style all laid down like that. And then he would go ahead and throw his 50. And then we'd plot it. I wrote a little computer program to plot them. And this is it. So you'd say the precision wasn't very good. But in fact, the precision in the x direction was fairly good because this circle represents what's called the standard deviation. It's a two-dimensional standard deviation. But in the y direction, the precision's horrible. And you can see the average is a little bit shy of the bullseye. So they weren't quite accurate. So now you got to come up with why weren't they quite accurate? Well, because of gravity. They weren't compensating for gravity. So they would throw the dart and they would aim for the bullseye rather than above the bullseye, and it would always land consistently lower than the middle of the bullseye. Now, they were pretty much throwing straight at the bullseye. So they had good alignment in the X direction. So they were actually accurate this way, but they were inaccurate that way. All right? And their precision was terrible. Why? Because my son, or this guy right here, David, they probably had never thrown darts before. So it's really hard to control your throw. And when you do that, you're going to have a lot of spread in your data. All right, so that's the background to the lab number 2, and we're going to come right back and I'm going to show you the experimental setup. So may the Lord be with you and keep you safe and healthy. Over and out.